Hello, everyone. As a physics teacher, I love digging into how the universe works. But what if one of the first things we all learned, that the universe started with a Big Bang and has been expanding ever since, isn't the whole story? What if it's just wrong? Today, we're going to walk through a completely different idea, and this explainer comes from the source material, the TriPhase physics framework, a foundation in wave mechanics. It paints a picture of a cosmos built purely on wave mechanics, with no Big Bang and, get this, no expanding space. So let's just start with that bombshell of a question. Seriously, just think about it for a second. We've been told for nearly a century that space is like a balloon being blown up, carrying all the galaxies along for the ride. But what if that's not what's happening? What if space is just space? What if it's static? Now, to even begin to answer a question that big, you can't just slap a patch on the old theories. The TriPhase physics framework says we have to go all the way back to the beginning. It's like building a house. You don't start with the paint color, you start with the foundation. And for physics, the true foundation isn't some complex abstract theory. It's the actual, measurable properties of empty space itself. This here is basically the blueprint. The entire framework is built step by logical step from what it calls the bedrock. These are the fundamental properties of the vacuum. And from that bedrock, basic wave mechanics gives us a core principle of stability. This stability then gives rise to something called a harmonic web, which is basically the cosmic scaffolding for everything from particles to galaxies. But you know what's really interesting? Look at what's not on this chart. There's no dark matter, no dark energy. In this model, you just don't need them. So what is this bedrock? Well, it's just three fundamental constants that we can measure in a lab. You've got permittivity, or epsilon zero, which you can think of as how much space permits electric fields. Then you have permeability, or mu zero, which is the same idea for magnetic fields. And finally, impedance, which is the vacuum's natural resistance to electromagnetic waves. The key takeaway here is that these aren't just numbers in a textbook. They are the physical rules of the road that dictate the speed of light and how all energy behaves. Okay, so you take those bedrock constants, you apply simple wave mechanics, and something really incredible emerges. If you look at these wave combinations, you can see that if you add 2 waves or 4, you get these chaotic spikes and dips. The system is totally unstable. But when you combine exactly 3 waves, each offset by 120 degrees, they perfectly cancel each other out. The total energy stays completely constant. This principle is called three-phase stability, and the framework proposes that this is the fundamental reason why stable particles, like the protons and neutrons that make you and me, are made of 3 parts. All right, so now that we have that foundation set, let's see how it totally changes our view of one of the cornerstones of modern astronomy, redshift. You know, the observation that light from distant galaxies appears stretched out. So the standard model on the left says redshift happens because space itself is expanding, which literally stretches the light waves traveling through it. But TriPhase on the right proposes a totally different mechanism. It says space is static. Redshift isn't from stretching space, it's because the photon itself loses a tiny, tiny bit of energy to the vacuum as it travels over billions of years. And this energy loss has a really fascinating effect on the photon's speed. The name for this process is photon wave packet deceleration. Now, I have to be crystal clear about something. This is absolutely not the old tired light theory. Those old ideas were debunked because they just said light gets tired and loses energy, which violated really basic laws of physics. This is a completely different mechanism, one that's rooted in a proven principle of wave mechanics that we're about to see. And here's that principle. It's called the Q balance. You see, a photon isn't really a dot, it's a wave packet. This packet has 2 speeds. The first is the speed of the whole envelope, the group velocity, which is what we usually think of as the speed of light. The second is the speed of the little wave crests rippling inside it, the phase velocity. As the photon loses energy, its overall envelope, the group velocity, actually slows down. And this isn't just theory. The Glasgow experiment proved that the wave packet doesn't always have to travel at velocity c. But to maintain a perfect physical balance, as the envelope slows, the phase velocity of the waves inside speeds up, so that their product always equals exactly c squared. So this is a very different way of looking at light, but it's not just a curiosity. It turns out that this one change might just solve some of the biggest, most nagging problems in cosmology today. Let's start with the Hubble tension. This is a huge crisis right now. When we measure the universe's expansion rate by looking at the very early universe, we get a number around 67. But when we measure it using stars in the nearby or late universe, we get a number around 73. The problem is these two numbers are supposed to be the same, and their error bars don't even overlap. It's a fundamental disagreement. So why don't they match? Well, the TriPhase framework argues it's because both teams are analyzing their data using formulas that assume the standard model of an expanding universe is correct. They're essentially baking the answer into the question. It's a circular argument. You assume your model is right to interpret the data, and then you claim the interpreted data proves your model is right. So, what happens if you just take the raw supernova data and analyze it using the TriPhase formula for photon deceleration instead? Well, you get this. The blue line is the TriPhase prediction, and it fits the raw data perfectly. And the Hubble constant it derives from first principles, 71.48. It lands right in between the other two values. This suggests the Hubble tension isn't some deep cosmic mystery, but maybe just an artifact of using the wrong model. This also helps explain another huge puzzle that's been in the news lately. The James Webb Space Telescope is finding these huge, well-developed galaxies that, according to the standard model, are so far away they should be from the early universe. They look far too mature for how old the model says they are. They've been nicknamed to be impossible galaxies. Well, in the TriPhase framework, they aren't impossible at all. You see, the standard model equates high redshift with the early universe and calculates a journey time for that light that's relatively short. But TriPhase says that high redshift just means the galaxy is incredibly far away. Because the light's wave packet was decelerating on its journey, it took billions of years longer to reach us than the standard model assumes. So the galaxies aren't impossibly old for their age, they're just old. They had all the extra time they needed to mature. We were just using the wrong stopwatch to time their light's journey. Okay, so this framework cleans up a couple of major cosmological problems. That's pretty impressive. But its real power, its real test, comes from its ability to make precise, verifiable predictions about the universe from the ground up. And we're not talking about just a few vague predictions here. The TriPhase framework mathematically derives the precise values for fundamental constants in particle properties of our universe. How many? 26. And this chart shows just how well it does. All 26 of these values, from the mass of the Higgs boson to the temperature of the cosmic microwave background, are calculated from nothing more than those three bedrock constants we started with. And all of these calculations have been mathematically verified to match the empirical data with incredible precision, usually within less than 1%. But here's the most important part. It's all done with zero fitted parameters. There are no fudge factors or magic numbers plugged in to make the math work. The framework either predicts the right answer from first principles or it doesn't. And the confirming evidence just keeps rolling in. Very recently, in 2024, a survey called DESI published new measurements for the vacuum's equation of state, a value known as W. Now, the standard model is very strict. It requires W to be exactly -1, but DESI measured it at -0.83. For the TriPhase framework, however, the prediction from pure wave mechanics was that W should be exactly -5/6, which is -0.833 repeating. The observation is a near-perfect match for the TriPhase prediction. So if there was no Big Bang, where did everything come from? This quote really captures the new cosmic story. The TriPhase model says that energy is always accumulating. The quantum fluctuations in the vacuum itself act like a tiny engine, an oscillator, that allows energy to slowly build up into harmonic nodes. Over immense timescales, these nodes form a harmonic web, which is how matter and energy clump together to eventually form the stars and galaxies we see. It wasn't a single explosion. It's a continuous process of creation. So if the cosmos isn't expanding, what does that really change? The TriPhase physics framework gives us more than just different equations. It offers a whole new narrative for the universe. It's a story that isn't about a violent, chaotic beginning, but about a gradual, continuous, and harmonic creation built logically from the very fabric of space itself. It suggests a universe that isn't flying apart into a cold, dark end, but one that is eternally and elegantly building itself. And that's, I think, changes how we see absolutely everything.